So over elementary regions. So again, the idea, guys, here is, so first we defined, we define double integrals over rectangles. So now the goal is to extend the definition of double integrals over rectangles to double integrals over elementary regions. Okay, so that's the that's what we are doing now, right? So this is the goal. We define double integrals over rectangles. So now we're going to extend double integrals over rectangles. So remember how we defined the double integrals over rectangles? We use Riemann sum, right? Over rectangles to double integrals over elementary regions. Right, so we do know what's the rectangle, of course. Now I'm gonna just remind you what's the elementary regions, how I introduced this elementary regions last week. So very quickly, I'm gonna remind you the definition. So there are two types of actually of elementary regions. So two types of elementary regions. All right, so first type 1. Yes, David. Yeah, I'm recording the session. Yes, sure. Type 1. So the elementary region D is, so D, the region D is the set, of Eric, you are here. Thank you. All right, thank you, Eric. I got you. So yeah, the first type, that's the set x, y, points x, y, says that so x is between two constant, a and b, right? And y is between two functions of x, let's say g of x and h of x. Of course, g and h both are continuous function on the interval ab. So this is the first type. And again, the idea is, so you're going to get regions of the following shape. So the idea here is that type 1, so you're going to get regions of the following shape. So first, so you have this is x-axis, y-axis, right? Your x, so we are saying x is between a and b, right? So here's your a, here's your b, okay? And at a, you're gonna have like let's say a segment, all right? And at b, the same thing. You're gonna have another segment, okay? And then of course, to connect the two segments, you're gonna have the graph of two functions. So in the bottom here, let's say you're gonna have g of x, and in the top here, that's h of x. All right, so this is a type 1 region. Okay, or instead of a segment, you can have like just a point. So for example, another example of type 1 region is again, you have a and b. All right, so again, because that's your x is between a and b. Right, so this is x, y-axis, right? So at a, let's say you have a segment, all right? And at b, you're gonna have just a point, okay? Now you're gonna connect the segment to the point. So in the bottom, you're gonna have this function g of x, right? And in the top, you're gonna have this function h of x, right? So that's a type 1 region, right? Type 2 region is, it's when your y is between two constant. So type 2. So that's type 1, type 2. Right, so the region D is the set of points x, y, so which satisfy the following. So your y is between two constant, C and D, right? And your x is between two functions, right? Let's say G, two functions, of course, of y. So x is between G of y and H of y, right? And so the idea here, so you're gonna get the following regions. So now at the y-axis, your x-axis, this is your y-axis. Now your y is between C and D, right? So let's say you have a C here, some D here, all right? So at C, you're gonna have a segment, right? And at D, you're gonna have another segment, right? And then, again, you're gonna just connect the two segments using these functions, G of y and H of y. So you're gonna have, let's say this is here, this is G of y, right? And this is H of y, right? So the difference, guys, here, again, so this is a segment, right? This is, this is just a line, a straight line, all right? So it's just a constant, right? Remember, we said, so for example, if you have a horizontal line, the equation of a horizontal line would be y equals to a constant. So for example, this line here, this horizontal line, the equation of this horizontal line is y equal to d, right? Because each point here lying on this line, right, the y coordinate is equal to d. The same here, the line here in the bottom, the equation of this line or the segment is y equals to c, right? Because if you take any point which lies on this line or this segment, the y coordinate is equal to c, right? Now, so we have a straight line in the bottom and in the top. Now, when you connect these two segments or two lines, you're gonna use actually some graph, a graph of some function, right? So this is a graph of the function h of y, and here this is the graph of some function g of y. It's not, it's not necessarily a straight line, right? Of course, instead of a segment at C or at D, you can have a point. So, for example, again, here's the y-axis, x-axis, and here's your C, here's your D. So you can have, for example, a point at C, a point at D, and then you're gonna connect these 2 points. So you're gonna use the graph of 2 different functions. Here's g of y, and here's h of y, right? And so your region D, of course, would be the interior of this, right? That's your region D. That's a type 2 elementary region, right? Anyway, again, guys, feel free to interrupt me. If you have any question, please unmute yourself and you can ask your question, all right? All right. Now, yeah, so we had an exercise last week, right? Exercise. So let me just remind you the exercise here. Exercise. So first, you have to determine whether D is an elementary region and the type of D. So is the region is the region T elementary? Right, and what type? And then, of course, sorry. And then, of course, you have to describe the region D, right? So, and then 2, describe describe D. Okay, so I think the first region was like a triangle. Okay, so 1. So we had this triangle. I think one of the vertex is the origin, right? So so this is your x-axis. This is your y-axis, right? This is 0. This is, let's say, this is the point 1, 0. This is the point 0, 1, right? And so we have here a triangle, a right triangle, right? So so our region D is this one here, the interior of this triangle, right? So D in this case is the interior of a triangle. Right. Okay, guys. So now we have to determine whether D is a elementary region or not, right? So and what type. So for example, you can, let's say, start with X. You know, your X coordinate, and you can try to see if your X coordinate is between you know, two constant. Okay, and of course you need to have, like, at each constant you need to have like either a segment or a point. So for example, if you start with the X coordinate, your X coordinate here, you know, at 0 you have this segment, right? So this is X equal to 0, right? Because, you know, the y-axis, or this segment here, each point of this segment, right, the X coordinate would be equal to 0, right? And then at 1, you have this point, X equal to 1, right? So what we are saying is, like, we have a segment here and we have a point here, all right? And then remember, guys, all we have to do then is just to, you know, use the graph of two functions to connect the segment to the point. So I'm going to connect this, you know, this segment here to this point. I'm going to use here, let's say, g of y, and here I'm going to use h of y. Right? So here, this is x equal to 0. Here at this point, x is equal to 1, right? So your x is between, you know, 0 and 1. Now, what about, sorry, this should be a g of h and a g of x. This is g of x and h of x. Now, what about g of x and h of x? Well, g of x is just, here's my g of x. It's just a straight line, right? This is my g of x. Okay, so my g of x would be just the x-axis, right? And what would be the equation of the x-axis? Well, it's just, you know, y equal to 0, right? I mean, any point which lies on the x-axis, the y coordinate would be 0. So g of x is just equal to the function 0. Okay, because that's your, you know, that's your x-axis. And that's the equation of the x-axis. The equation of x-axis is y equal to 0. So in the bottom here, we have this function g of x equal to 0. Now, in the top, I have this h of x. So my h of x here, it's also a straight line. It's not, of course, it's not the horizontal line, but, you know, it's a straight line. Now the equation, the question is, what's the equation of this straight line? Or what's the equation of this function here? Well, this is just a, you know, this is a straight line which connects these 2 points, the 0, 1 to 1, 0, right? So we have to find the equation of this line. So this line here, so h of x, it's a line which connecting 0, 1 to 1, 0. Okay, so the question is, what's the equation of the line which connects 0, 1 to 1, 0? Well, I mean, you can find the slope first, right? You know, so the form or the equation of the line would be of the form y equals to ax plus b, right? So a would be the slope. You know, I guess you know how to find the slope of this line here. So you can just subtract, you know, the y coordinates. So you are going from 0, 1 to 1, 0. So let's say it's, you know, 0 minus 1 over 1 minus 0, right? So the slope is just -1. Right, and then you can just, you know, substitute x and y with the 0, 1 or 1, 0, and then you can find b, right? So then, let's say I'm going to use substitute you know, let's say y by xy by 0, 1. So then you're going to have y is equal to 1 equal to a, which is -1 times x. X is 0, right? Plus b, right? So then b is 1. Okay. Anyway, so the conclusion is that the equation of this line, which connects the point 0, 1 to 1, 0, is just y equal to minus x plus 1. Okay, so all I'm saying, guys, here is that this line here, this one here, is the line y equals to minus x plus 1. So that would be my function h of x. So y is equal to h of x is equal to minus x plus 1. Right? So, you know, so my y coordinate is supposed to be between g of x and h of x, right? That's the definition of, you know, type 1 region. So your y in this case, so g of x, we said it's just this, the x-axis, right? It's just y equal to 0 or g of x equal to 0. So here's my 0, and h of x is just this straight line here, right? This is minus x plus 1. So here's minus x plus 1. Right, so all I'm saying here, guys, is that so my x would be between 0 and 1, and my y is between 0 and minus x plus 1. So this is type 1. So this is a type 1 region. So to answer the question, so the answer. So this the interior of this triangle is a type 1 region. Type 1. So we can write D as the set of, you know, the points x, y, says that x is between 0, 1, right, and y between 0 and minus x plus 1. Right?
Excuse me, Professor.
Yes. Please go ahead.
Can it be type 2 also?
Yes, it's actually type 2. That's my next remark. Absolutely. Very good point. That's a very good point, because so instead of so we have this triangle. Absolutely. So we have this triangle. So this is again 0, 0, 1, 0. This is 0, 1. All right. So instead of, so here's my x-axis, and this is my y-axis. All right. So instead of using the x coordinate, I'm going to start with the y coordinate. Okay. So I can say that, like here in this case, my y coordinate would be between. So here's 0. You have this line here in the bottom. the segment here in the bottom, right? And you have this point here in the top here, right? So this is y equal to 0, right? And here, of course, y is equal to 1. Okay, so I have a segment in the bottom, I have a point in the top, and now I'm going to connect them. So when you connect them, so here, I'm going to use this line, all right, to connect my segment to this point. And of course, so this line, it's just a line with the equation x equal to 0. All right, and so that will be my, that will be my, let's say g of y, right? And here, this line here, that will be my h of y. Okay, and so h of y, in this case, it's a function of y, right? So here, my x would be equal to, I mean, we said y is equal to minus x plus 1, right? So then x would be equal to 1 minus y, right? So my function of y here, h of y, so h of y is 1 minus y, right? Because here we need a function of y. So h of y is 1 minus y. So yeah, absolutely. So this is, so D is also of type 2. Is also of type 2. Okay, because I can describe D as the set of the points says that, so your y is between, so we said y is between, 0 and 1. So we have the segment in the bottom and this point in the top, right? So y is between 0 and 1, and x is between the graph of two functions. So on the left, we have this g of y. It's just x equal to 0. It's a vertical segment. So x is between g of y, which is just 0 here. Right? And on the right side, I have this hypotenuse, right? That's h of y, which is 1 minus y. Right? Yeah, so actually D is of both type 1 and type 2. Very good point, Enrique, I think. Any other question, guys? So do you see how it works? I mean, type 1, you're supposed to have like, in the bottom you have like on the left you have like a segment, on the right you have another segment or a point instead of segment, right? And you connect the segment to the point or the segment to the segment using graph of two functions, right? Right, is there any other question, guys, about this first example? Or, I mean, the first question in the exercise. So it's a triangle, right? Now, for number 2, next region, I think we had a disk, right? So next example, number 2. So our region D, so D is the disk. So what do I mean by disk is the interior of a circle of radius 1. All right, of radius 1. So this is a 1 here, 1, negative 1, negative 1, x and y. So we have this circle. Right, and of course my region D would be the interior of this circle. This is my region D. Okay, so I have to determine whether this D of type 1 or type 2 or both. It could be both type, right? So well, let's say you start with x, right? So your x varies between well, you see your x, it goes from from -1 to +1, right? So x goes from -1 to +1, right? At -1, we do have just a point, right? It's just a point. It's not segment at -1. It's just a point. So I have like a point here and a point here, right? And I'm supposed to connect the 2 points using the graph of 2 functions, right? So here I have x equal to 1. Here I have x equal to -1. And then I'm supposed to connect these 2 points using the graph of 2 different functions here, right? Here, let's say g of x. And in the top, I have h of x. Right? Now, the question is, so what would be the equation of, let's say, of g of x? What's the equation of g of x? So this is supposed to be my g of x. All right. Well, I mean, this is just my circle, right? So what's the equation of the circle? Well, the equation of the circle, of course, is just it's just x squared plus y squared equals to 1, right? So this g of x, of course, when I say g of x, this is like saying g of x is just equal to the y coordinate, right? So I have to solve here. We need to solve for y. So we need to solve for y. Okay, because it's g of x, so it's a function of x, so we need to solve for y. So what will be y? Well, if you solve for y, of course, solve for y, you have y squared equal to 1 minus x squared. But then here we have to be careful, of course, because you have the even power, y squared. So we have even power. And of course, you want to get rid of the even power of the square, so we have to apply the square root, right? But when you apply the square root, because the power is even, right? So I'm going to apply a square root both sides. But because this is even, the power is even, then I'm going to need the plus or minus, right? So actually, your y, when you solve for y, when you solve for y, you're going to have y equals to plus or minus square root of 1 minus x squared. All right, so again, we have plus or minus because the power is even. If the power was odd, of course, there would be no plus or minus. Okay, so now we have this plus or minus. Now, for my g of x, the graph of this function here below the x-axis, is it plus square root of 1 minus x or minus square root of 1 minus x squared? Sorry. Below the x-axis is going to be negative, right? This is the y coordinate here below the x-axis. So here my y is negative. The y coordinate is going to be negative, right? Because we are below the x-axis. So what would be the equation of y? I mean, the equation of g of x. Well, my y, which is g of x, is just minus square root of 1 minus x squared, right? Now, that's my g of x. What about h of x, the top here? So this is, let's say, this is my function h of x, right? Which is y, right? That's my, so my y coordinate is equal to some function of h, h of x. Well, this is, of course, this is above the x-axis. So then it's positive. The y coordinate is going to be positive. So this is a plus square root of 1 minus x squared. Right? So all I'm saying, guys, is that, so in this case, so my x is between -1 and +1. So conclusion is that my x is between -1 and +1, and my y, so my y is supposed to be between the graph of 2 functions, g of x and and the h of x. Here's my blue. So here's my y. So in the bottom, below the x-axis, we have minus square root of 1 minus x squared. And above the x-axis, we have a plus square root of 1 minus x squared. All right. So then your d is, so we can say that d is of type 1. So d is of type 1 because we can describe d. So d would be the set of points x, y with x between -1, +1, and y, between negative square root of 1 minus x squared. I'm sorry. And so y between negative square root of 1 minus x squared and positive square root of 1 minus x squared. Okay. Of course, just be careful, guys. So these functions, plus or minus square root of 1 minus x squared, they are continuous on this interval. My x is, my x is supposed to be in the interval -1, +1. So these two functions here, they are, they're continuous on the interval -1, +1. Okay, so there is no problem with these two functions. They are both continuous on this -1, +1. So you have to make sure that these two functions, g of x and the h of x, they are continuous on their the interval, right? Because if, for example, if your x is, let's say, between -2 and +2, then there'll be a problem. There will be a problem with g of x and h of x because, of course, we cannot have a negative number and the square root, right? So if you have like x equal to 2, you're going to have this negative number in the square root, and that will be a problem, right? Because your function, it's not defined for x, for example, for x equal to +2 or -2. Anyway, so d is of type 1, but also actually d is also of type 2, right? Because we can do the same thing, but instead of starting with x, again, I can start with y. We still have our circle. Here's my circle. I can say, well, here in the top I have y, so y equals to 1. Here in the bottom I have y equals to -1, right? So I have this point here in the top, I have this point here in the bottom, and I'm gonna connect them using the graph of two functions. So here I'm gonna go with, let's say, g of y, right? And here this is h of y. Okay. And actually, so this is g of y here, and here's h of y. And the interior would be my region D, right? That's my region D. Right? Now, what will be the equations of g of y and h of y? So when I say g of y, that's equal. This is supposed to be equal to x. So x is equal to g of y, and x is equal to h of y. So we have to solve. Again, it's just my circle. But then in this case, we have to solve. For x. Okay, because I need to find the equation of x, right? X is equal to some function of y, right? So if you solve for x, of course, then we're gonna have the same thing. It's plus or minus 1 minus 1 minus y squared, right? So on the left here, on the left, of course, the x coordinate on the left is negative. So x here is negative on the left. So it's going to be just minus square root of 1 minus y squared. And on the right, the h of y, x is positive, right? Here your x is positive, right? So x is positive on the right side. The x coordinate is positive on the right side. So my x would be equal to plus square root of 1 minus y squared. All right. So we can conclude that the D is also of type 2. So D is also of type 2 because, so we can describe D as the set of points x, y. So your y would be between, -1 and +1, and x between these two functions, g of y and h of y. So x is between, negative square root of 1 minus y squared and positive square root of 1 minus y squared. Right? So D is of both type 1 and type 2. The same same thing like for the triangle. Right? Is there any question, guys? I mean, I hope you see how it works, right? I mean, so you can, for example, start with x, and then at x, on the x-axis, you need to find like a point or a segment on the left, and a point or a segment on the right, and then you need to connect the segments, or the point to the segment, or the 2 points, right? Etc. Anyway, so I think for question number 3, we had another triangle, but anyway, it's the same. The idea is the same, right? It's just it's just a different triangle for number 3. So let me just write down here number 3. Number 3 was a triangle. X-axis, y-axis, and we have this triangle. This is this vertex of coordinates 1, 1. This vertex is with coordinate 4, 1, I think, and this vertex is with coordinate 1 and 2. Right? And of course, our region D is the interior of this triangle. Right? That's our region D. Anyway, okay, so it's the same thing, almost the same thing as the first example. So this region D, the interior of this triangle is going to be also of both type 1 and type 2. You have to compute, well, I mean, the equation of this line here. This is just a horizontal line. So the horizontal line, then the y is a constant. So here y is equal to 1, right? This is 1 here. So we have also this this line, right? This is it's a vertical line. The x coordinate here is 1. So this is x is equal to 1, right? And then of course, this is the hypotenuse, and you have to find the equation of the hypotenuse. Again, guys, all you have to do is, as I explained in the first example, you have to find the slope A and then B, and then you can find the equation of your line, right? It connects these 2 points, right? The 4, 1, 2, 1, 2. Anyway, so if you do the computation, then I think the equation of this line would be y equals to minus 1/3 of x plus 7 over 3. Okay. Or if you want to solve for x, that would be x equal to 7 minus 3y. Okay. Anyway, so if you want to describe D as of type 1, so if you want to describe D as of type 1, so of type 1, you start, again, you start with x. So you check the variation of your x. So x, here's my x-axis, of course. So x goes from, from 1, from here, this is 1 here, to this point here, which is 4. Okay, so your x belongs to this interval 1, 4, right? So x is between 1 and 4. Now your y, so I have a segment here, I have a point here on the right side, and now I'm going to connect this segment to this point. I'm going to use a function in the bottom here and another function here in the top. So this would be this is g of x, and in the top I'm going to have h of x, right? Y equals to h of x and y equals to g of x. Now in the bottom, y equals to g of x, that's exactly y equals to 1. So that's my g of x, so that's equal to 1 here. And in the top, right, that will be the hypotenuse. That's y equals to negative 1/3 of x plus 7/3, right? So your y is between these, the graph of these two functions, g of x and h of x. So y is between 1 and negative 1/3 x plus 7/3. Okay. And so it's of type 1, or you can also say that D is actually of type 2. It is also of type 2. So in type 2, you start with y. So I'm going to start with y. So y, in this case, so my y coordinate, it's between, you see here, so my y coordinate is between 1 and 2. Right? So at 1, I have this segment, and at 2, I have this point. All right, so y, so this is, y equals to 1, and here you have y equals to 2, so y between 1 and 2. All right, and then I'm going to connect these two, the segment to the point using the graph of two functions. So here I have first function, that's my g of y, and here's my h of y. So this g of y, which is equal to x, this is h of y equal to x. So g of y here would be equal to 1, and this h of y, which is x, if you solve for x, we said we would have x equal to 7 minus 3y, right? So this is 7 minus 3y. So what we are saying here, guys, is that x would be between this g of y and h of y. So x is between 1 and this 7 minus 3y. Right? So that's why D is also of type 2. Right? Any other, is there any question, guys? Anyway, so on all these examples, all these regions are actually of both type 1 and type 2. I think the last question was about the annulus. So we have this ring, number 4. So this is very interesting, actually, a very interesting question here. So number 4, D is, so it's a different different region here. It's not a disk, it's not a triangle, it's an annulus, right? So D is, is the annulus. Bounded between the two circles of radius 1 and radius 2, right? Between x squared plus y squared equals to 1 and x squared plus y squared equals to 4. All right, so we have, this is a circle of radius 1, and then we have a circle of radius 2. All right, and so my region D is bounded between these two circles. So my region D is this ring shaped area, right? This is my D. Right. So again, here, this is 1, this is negative 1, and here's negative 2. Right? So the question is D in an elementary region, right? So for example, let's say this is x-axis, of course, this is my y-axis. So there's a problem here, guys, because you know, so you start with x, right? Let's say you start with x. So x varies between you know, from it goes from -2 to +2, right? In some sense, right? Um, so you may say, well, my x, you know, my x, so this is -2, this is +2. All right, so my x, so if you take any point here in this annulus, right, then the x coordinate, you know, would be somewhere between -2 and +2, right? But then remember, so we have 2 points here, and now what we have to do, I mean, if you're gonna get an elementary region, you have to connect these 2 points using the graph of 2 functions, right? So for example, here in the bottom, we're gonna use some function, let's say g of you know, g of x, and here in the top, you're gonna use another function. Here, let's say h of x, right? You have 2 points or like 2 segments or a segment and a point, and you have to connect them using the graph of 2 different functions, right? And the interior here would be your region D. But here there's a problem because, you know, actually there are like 4 different graphs here. It's like, you know, you have this, this is first graph here. This is, so this is above the x-axis, right? So this would be the equation of this. The graph here would be, let's say, you know, square root of positive square root of 4 minus x squared, right? Your y is equal to positive square root of 4 minus x squared, and you have another graph here, this one here, right? That's your positive square root of 1 minus x squared, right? Now, below the x-axis, you're going to have also 2 different graphs. So you're going to have this one here. That will be negative square root of 1 minus x squared, right? The y coordinate is negative when you are below the x-axis. And you have another graph, which is, you know, this one here. And this would be negative square root of 4 minus x squared. So in this example, so what I'm saying is like you have like 4 different graphs, right? It's not just two graphs, it's 4 different graphs, right? Plus or minus square root of 4 minus x squared and plus or minus square root of 1 minus x squared, right? So it's like kind of we have like 4 different graphs here, not just 2, but 4, right? So that's why actually in some sense, that's why your D, it's in this example, D is not an elementary region. So in this case, let's say in this example, like we have more than 2, we have like 4 different graphs of functions, right? Not just 2. Okay. And of course, you can do also the same with the, instead of you know, starting with x, you can also start with y. You can say, well, your y is in the top. I have y equals to 2. That's like the highest point, y equals to 2. In the bottom, lowest point would be the y coordinate would be y equals to -2, right? But still, you're gonna have like 4 different graphs, like plus or minus 4 square root of 4 minus y squared, and plus or minus square root of 1 minus y squared, right? And so actually the conclusion in this case is that the D is not elementary region. It's not an elementary region. right? And but actually, I'm gonna probably leave this in this for the homework. We can describe this D as actually the the sum of four different elementary regions. So probably gonna leave this for the homework, but let me just remark here that D, we can describe D. D itself is not an elementary region, right? So D, we can describe D as the sum of four elementary regions. Okay. So I'm going to leave this for the homework. But I mean, so the idea is to divide. We can divide. So what I claim here is that we can divide D. We can divide D into four elementary regions. Okay. Well, I mean, do we have time to do it right now, or I'm gonna leave? Probably I'm gonna leave for the homework. But actually, this is a really good exercise for the homework. Anyway, is there any question, guys? I mean, I can give you probably, sketch for you the four different regions here, but I mean, it's up to you. Okay, so probably we should do another exercise because I know this elementary regions is not, I mean, this is not, I would say it's not an easy notion. Sometimes it just take time to understand this idea of the elementary region. But anyway, so here's an exercise so you can practice a little bit. So exercise. So I'm gonna do in this what I'm gonna do in this exercise, guys. We're gonna try to sketch the region D. So so the exercise is to sketch the region D. Okay, so for example, number one. So the region D, let's say D is the set of XY. Let's say X is between 0 and 3, all right? And Y between minus X and positive X, okay? So all you have to do, guys, is just try to graph, or sketch this region D, all right? Another number two, let's say 2 here. So let's say D is the set of XY says that, let's say X is, or Y, let's say Y between 0, 1 and X between, let's say Y squared and Y. Okay. So all you have to do, guys, is just to sketch the region which corresponds to this set of points here, right? So I'm going to give you, let's say, 5 minutes to think about this exercise. Yeah, by the way, guys, probably I'm gonna assign the first homework so this Thursday. I think probably today we're gonna finish. Well, hopefully we're gonna finish this double integrals. So next thing we're gonna do, of course, is the triple integrals. So if we finish, yeah, I guess we're gonna finish the double integrals today, and then so I can probably assign the first homework on Thursday. Zivolod, you are here. I see you are here. Because I take the attendance, so I need to know if you are here, guys. All right. So So in this exercise, the first region, so x between 0 and 3 and y between minus x and positive x. So in the first region, that will be a region of type 1. For the second region, where y is between 0 and 1 and x between y squared and y, that will be a region of type 2. All right, so what I'm saying, guys, so this is of the first one here, this is of type 1. And this one here, it's type 2. So any guess what will be the shape of the first?
It will be a triangle.
Yes, absolutely. Thank you. Enrique, right?
No, it's 7.
Oh.
And the second one has the shape, I don't know how it's called.
Yeah, it's not. It's yeah, it's not like geometric.
It's yeah.
Yeah, yeah. All right. So yeah, that's very good. So for the first one, oops, sorry. Yes. So for the first region, right. So here's my x-axis, y-axis. So first x is between 0 and 3, so I'm gonna need, I guess, 0, 1, 2, and 3 here, right? So when you say x is between 0 and 3, it means that x is between the graphs or the functions x equal to 0, right? So x equal to 0 and x equal to 3, right? Here, so x equal to 0, and here's your x equal to 3. X equal to 0 would be a a vertical line, so which is just the y-axis, right? So here my x is equal to 0, right? Again, guys, because if you take any point on this line, the x coordinate would be equal to 0. Now there's x equal to 3. Same thing. You can just take the line passing through x equal to 3, right? So here's my line x equal to 3. So when you say x is between 0 and 3, it means that x is between these two lines. So this region here, this corresponds to the region where x is between 0 and 3. Right? Now, next, what about y? So y, in our case, here's y. So y is between negative x and positive x, right? So you have to graph the function. So here y equals to minus x, and here we have to graph the function y equals to positive x, right? So let's graph y equals to x. So let's say this is 1, 2, 3 here, let's say. All right, so y equals to x. So it would be this the diagonal, this diagonal here. This is y equals to x. All right, and then there's y equals to minus x. I'm probably going to need -1 here, and here is y equals to negative x. Right, this is, here's -3. So this is line y equals to negative x. Right, now the question is, which region corresponds to y between negative x and positive x? So when you say y, so y is larger than negative x, right? So first, so we are saying y is larger than negative x. This is, again, this line here, this one, this is y equals to negative x, right? So y larger than negative x would be either this region here, on the, like, I would say the right side of the y equals to negative x, or this region here on the left side of y equals to negative x, right? So y is larger than negative x. I mean, there are different ways actually to figure out which region is the y is larger than negative x. You can, for example, guys, just take a point. So for example, if you take this point here, this is the point, let's say 0, 3, right? X is 0, y is 3. So x is 0 and y is 3. Is 3 larger than -0, which is 0, of course? And yes, it's true. 3 is larger than 0. So if 3 is larger than 0, so which it means that our inequality is satisfied. So the y larger than -x would be this. So would be this side of would be this side here. this one here. All right, that's why this is y larger than negative x. Okay. Now we have, so now there's another inequality, right? Y is less than x. So y is less than x. Okay, so this is the diagonal here. This is y is equal to x, right? This is y is equal to x. Now, y is less than x would be either the region, this one here, you know, on the, let's say the left side, or, left side of y equals to x, or the right side of y equals to x. And again, all you have to do is just take a point. Just to take a point, for example, take a point. Again, let's just take the same point, the 0.03, this one here, the 0.03. So y is equal to 3, x is equal to 0. That's, of course, 3 is not less than 0. So this is false, right? So the region which corresponds to y less than x would be this one here. Right? So this is where y is less than x. Okay. Again, guys, this is y equals to x, so it divides your plane into, you know, two different regions, right? The one on the left and the one on the right. So all you have to do to check which one where y is less than x, take a point, check the coordinates of the point if they satisfy the inequality, right? Now, what will be the intersection of all these regions? What will be the intersection of the green, yellow, and the blue regions? Well, the intersection would be this one here. You see this one here, this region here. It's at the same time green, blue, and yellow, right? So we get this triangle here. All right. So that's my my region D. Okay, so that's the region D. Any question, guys? How I got this region D? Nope. Okay, perfect. All right. So for that's number one. Number two. So for number two, we have D is. So D is the set of points x, y, says that. So we said y is between 0 and 1, right? And x is between y squared and y. All right. So first, so I'm gonna start with y between 0 and 1. So I'm gonna draw or graph the functions y equals to 0, y equals to 1. So we have to graph y equals to 0, y equals to 1, right? Because your y is between 0 and 1. All right, so x-axis, y-axis, y-axis. So let's say this is 1, this is 2. So this is, let's say, 3, 4. Let's say this is 1, 2. All right. Anyway, so y equals to 0. That's just the x-axis, right? So this is my y equals to 0. That's my my x-axis. Now y equals to 1. That will be this horizontal line. This is y equals to 1, right? So my y coordinate is between 0 and 1. So it means that will be the set of these points between these two horizontal lines, right? That's where y is between 0 and 1. All right, so this is where y is between the y coordinate is between 0 and 1. Now, next, we have to graph. So we have to graph. So we have x between y squared and y. So we have to graph first x, or y squared is equal to x, or x equal to y squared, right? So we have to graph this function here. It's a function of y, right? It's not a function of x. So x is equal to y squared. For example, if x is 1, of course, y would be, if y is 1, x is 1. Let's say, so we're going to have this point here. Let's say if y is 2, x is going to be 4. If y is 2, x is 4. So it's somewhere here. Right, this is 4, 2, right? And this is 1, 1. Anyway, so we're gonna have, we're gonna have a parabola, right? Of course, as a function of y, not of x. So we're gonna have this parabola here. X is always positive, of course. All right, so this is the graph of y squared equals to x, or x equal to y squared. Right. Now, we need x. So we need x to be larger than y squared, right? So we need x, come on. So we need x to be larger than y squared. So we have this yellow parabola, right? So this yellow parabola divides your plane into two different regions, right? So you have this, the interior of the parabola and the outside, let's say, of the parabola, right? So we have to figure out which region corresponds to x larger than y squared, right? Is it the inside of the yellow parabola or the outside of the yellow parabola? Well, all you have to do, take a point again. Just take a point. For example, this is the point. This is the point 2, 0, right? Your x is 2. Your y is 0. Now, is 2 larger than 2 squared? Yes, it's true. Right? 2 is larger than 0 squared. So then the corresponding region to x larger than y squared would be this one here. So this is where your x is larger than y squared, right? So this is where x is larger than y squared. Next equation. So we have x less than y. So we have to graph x equal to y. It's just a straight line. So it's going to be this. So it's going to be this line here. Right. So this is where y is equal to x. Right. Now we need we need x to be less than y. So we need x to be less than y, right? Okay, so we have this diagonal. So the diagonal divides your plane into two regions, the one on the right or the one to the left, okay, in some sense. So which one is where corresponds to x less than y? Again, just take a point. You can just take this point to 0. There x is 2, the y is 0. Is 2 less than 0? No, this is false. Okay, so the region which corresponds to x less than y would be the one to the left. So that would be this region here. So this would be, so this is where x is less than y. Okay. Now, if you take the intersection of all these regions, the blue, the yellow one, etc. So then the intersection would be this very small region here, this one here, sort of this one here, right? So that will be, so that's our region D. Okay. Any question, guys? All right, no question. So anyway, so why we are doing all of this? Why we are studying these elementary regions? It's because now, now the main theorem is that we can extend our double integrals over rectangles to double integrals over elementary regions. So here's the theorem. So why we are doing all of this? Because of the following theorem. So if if D is of type 1, so X between A and B, Y between G of X and H of X, right? Of course, G and H both are continuous on the interval AB, and you have some function F and F of XY, right? Continuous function, continuous over this region D. So then, the integral, so this function here, of course, this is continuous on this region D. Then the double integral of f of xy over this region D, okay? This is a region of type 1. Of course, integral with respect to the area element, dA. So that will be equal to the double integral. So we're going to have f of xy. So our area element is just dx dy. But here, your x is between a and b, your y between g of x and h of x. So we need to use actually dy dx here. So we have to start by integrating with respect to y first. So dy dx. So y is between g of x and h of x, and x is between a and b. Okay, so what I'm saying, guys, is that if you have a type 1 region and you have some function continuous on this region, then the double integral over the region D would be the integral, double integral with respect to the area element dy dx. So first you integrate with respect to y, and then you integrate with respect to x. Okay. Now, if you have a type 2 region, elementary region, so if D is an elementary region of type 2, so y between two constant, c and d, and x between two functions of y, let's say g of y and h of y. And again, you have this function f continuous on this region D. Then the double integral of f of xy with respect to the area element over this region D, that will be equal to, so double integral, you integrate first with respect to x between g of y and h of y, and then you integrate with respect to y is between c and d. Okay. Well, we can prove this theorem, but before the proof, I mean, we can first probably do some examples, right? Let me do a numerical example, and then we'll see how it goes. All right. So examples. So let me let me use let's say D is the triangle so this is a 0, 0. This is 1, 0. This is a 0, 1. Right, and so our region D is just the interior of this triangle, right? So we said D would be of type of both type, right? Type 1 and type 2, right? So we can describe D as XY, right? We had this example earlier. So if you want to describe, and this is of course, so this line here, this is the line Y equals to minus X plus 1, right? Or if you want to solve for X, so that would be X equal to 1 minus Y, right? Anyway, and this is, so here, this is X equal to, sorry, this is Y equal to 0. And this is, of course, X equal to 0. Anyway, so if you want to describe D as type 1, we said then X would be between 0 and 1. Okay, and Y between 0 and minus X plus 1. Right? I mean, we had this example in the first exercise today, right? And so this is a type 1. So if you want to describe now D as a type 2, so then Y would be between 0 and 1, and X between 0 and 1 minus Y. Anyway, so we have this region D, and so now the example, in this example, we're going to compute, or we're going to evaluate a double integral. So the exercise is to evaluate. So we're going to evaluate the double integral of the function. Let's say we have this function xy squared over this region D, right? With respect to the area element. Okay. So I want to evaluate this integral using two different ways. Okay. So what do I mean by using two different ways? Well, because you can see, or you can describe the region D as a elementary region of type 1 or as an elementary region of type 2. So if you describe D as elementary region of type 1, okay, so first, so we can evaluate this integral if you describe D, so D of type 1, so D is just so we have X between 0 and 1, and Y between 0 and minus X plus 1. Right? So then your double integral over D, xy squared, dA. So in this case, if it's of type 1, so our theorem, it says that, so in case of when D is of type 1, so in case of type 1, first you need to integrate with respect to y, right? So it's dy first and then dx. Okay, so type 1, dy first and then dx. So dy first. xy squared. So dy first and then dx. That's because we said it's a type 1, right? So your y, so you start by integrating with respect to x, with respect to y first here. So your y is between 0 and minus x plus 1, right? So it's between 0 and minus x plus 1, right? And then the variable x is between 0 and 1. So here's my 0 and 1. All right, so you if you integrate with respect to y, so here with respect to y, assuming x to be constant, right? So then that will be equal to, so we keep the 0, 1 here, the dx, right? So you integrate with respect to y, x is supposed to be constant, so this is a constant here. So don't worry about the constant, just forget about the constant. And all you have to do is to integrate the y square, right? So integral of y square, of course, that will be y cubed over 3. So this is y cubed over 3, and here's my constant x. So this is evaluated between 0 and minus x plus 1, right? So we have to substitute y by minus x plus 1 first, and then by 0, right? So well, here probably there will be a lot of computations here. Let me see. Well, probably, guys, instead of y squared, I would just do just y here. Well, anyway, we can just continue here. Anyway, so it's just a lot of computations here. So it's going to be 0, 1. So x, substitute y by minus x plus 1. So this is minus x plus 1 cube over 3, right? Minus, and then you substitute y by 0. So it's x times 0 cube over 3, right? And there's the x here. So that'll be equal to integral 0, 1. So we're going to have x over 3 times this 1 minus x cube. All right. So we have to integrate with respect to x now, right? So here, I mean, there are different ways. I mean, you can distribute, or you can use probably integration by parts, or it's up to you. Okay. Probably it's gonna be just take a lot of time to complete this, so I'm gonna just leave this. So again, you can just distribute, or you can use distribute, or you can use integration by parts. Okay. Anyway, so you have to integrate with S to L to X, and then you can get your answer. Now, the other way to compute this integral, so if you describe now D as of type 2, number 2, so if you describe D of type 2, right? So we said, so then your D would be can be described as the set of xy, set of points xy, where y is between 0, 1, right? And x is between 0 and 1 minus y. All right. So then our double integral xy squared over d. So when we have a type 2, right? So first you integrate with respect to x. So here's, you see this is a type 2. This is a type 2 elementary region, right? So first we integrate with respect to x, and then we integrate with respect to y, right? So first with respect to x, and then with respect to y. So here, so we're gonna have xy squared, first with respect to x, and then with respect to y. So then your x is, your x is, we integrate with respect to x first, right? So your x is between 0 and 1 minus y. So here's 0 and 1 minus y. Okay. And then you integrate with respect to y, right? So your y, sorry, your y is between 0 and 1. So here's my 0 and 1. All right. So, sorry. So you integrate with respect to x. So with respect to x first, assuming y to be constant. Right. So this is, so that'll be equal to, again, 0, 1 here. Here's my dy. Here, y is going to be constant. So then y squared is constant. We don't worry about the constant. So all you have to do is just to integrate this x. So integral of x, of course, will be x squared over 2 times the constant times the y squared. So this is evaluated between 0 and 1 minus y. All right. So that will be equal to 0, 1. So we substitute x by 1 minus y. So here's 1 minus y squared over 2 times y squared minus, and then we substitute x with 0, right? So it's just 0 squared over 2 times y squared. There's dy. All right, so of course this is just 0. This is just 0, right? And then, so we're gonna have just the integral from 0 to 1. We're gonna have half 1 minus y squared over 2 times y squared dy. Now we integrate with respect to y. Again, here, guys, you can just distribute. You compute 1 minus 1 squared times y squared, etc., etc. It's a lot of computations here. So what I mean here by distribute, again, it's just you 0, 1. You say here's half 1 minus y squared. That will be 1 plus y squared minus 2y, times y squared dy, and then you multiply by y squared. 0, 1 half here times y squared times y squared times y squared here dy. You integrate and etc. etc. Right? So I'm gonna just leave this. It's just a lot of computations here. In theory, you know how to integrate in general, but anyway, so this is just the computations here. So I'm gonna leave this as the exercise, right? Anyway, so you get the same. So of course, we get the same answer as the first way, right? So we are supposed to get the same answer in both ways, right? So what we are saying here, guys, is that so if you have a region which is of both type 1 and 2, so there are two different ways actually to evaluate your integral. So you can describe D as a type 1. So if you describe D as type 1, you integrate first with respect to y, right? If you describe D as type 2, you integrate with respect to x first, right? I'm going to show you why this is kind of, it can be very, very useful sometimes. But before that, probably, okay, we have 10 minutes. So probably going to give you an exercise just to evaluate, integrals using two different ways, the same, similar to the example here. And then I'm going to explain why this is sometimes very, very useful, all right? Yeah, so here's an exercise, a small exercise, a similar exercise. So let's say D is equal is this triangle here. This is 1, 2, 3. This is, let's say, This is one here. This is a y-axis, of course. This is the x-axis. And let's say we have this triangle. So this is the point. This is the point 3, 1, of course. This is 0, 0. It's just 0, 0. Is this different from the example? Let me just see here. Our previous example was just, yeah, the triangle with the vertices 0, 0, 0, 1, and 1, 0. Okay, so it's kind of different triangle, at least. But anyway, so, all right, so my region D is the interior of this triangle, this one here. Okay, and so what you have to do, guys, in this exercise is to evaluate. So I'm going to just pick a very simple function here, just let's say just a function x. So then the integrals are very easy to compute. So x, the function x over this region D, okay, using, again, two different ways. Okay, again, this dA, that's the area element, right? This is the area element here. All right, and the x, that's my function f of xy. This is my function f of xy. All right, guys, so let's say, well, let's say you have 5 minutes. Well, anyway, we only have like 5 minutes. So let's say you have 5 minutes to think about this exercise. So again, guys, probably on Thursday I will assign first homework. Actually, I think there are a lot of different exercise you can have in the homework. This is, I mean, this double integrals. I mean, there are a lot of things that we can do. And as I said, after double integrals, we'll move to the triple integrals. And yeah. Yeah, after this exercise, I will show you why this is kind of sometimes very useful to have this two different ways to compute such as double integrals, because sometimes it's not easy to compute an integral. So sometimes it would be a good idea actually to to change the order of integration and to use a different order of integration. So yeah.
I've got 3, but I know that it's not the right answer.
Why it's not the right answer?
I think so, because it seems like that it should be 3/2.
Uh, because you think that the answer here should be the area of the triangle?
Yeah.
Well, oh yeah, okay, that's a good point. So you're gonna get the area of the triangle if you integrate the function one, right? Here it's not the function one, so um, I think I discussed this last time, but if you have the double integral over d of the constant function one, right? This would be the area of your region D. Okay.
Oh, I
But
got it. Yeah.
but if you have a function, some function here, that would be actually that's supposed to be the volume or the net volume. So in this case, so let me just show you here. In this case, you have this region D, wherever D here. Here's my D. All right. And you have this function f of xy, which is not the function one. You have this graph of this function f here, right? This is f of xy, right? And so this graph, this red graph, is supposed to be the image of your region D by the function f. So then this double integral, that will be the net volume of this solid, right? Bounded between the graph of f and your region D, right? Um, the, the the volume of this solid here, that will be the double integral of this function here. Right?
Yeah. Okay, I see it. Thank you.
But if the function is one, then you're right. That would be the so probably your answers are correct. Actually, three.
Yeah.
I don't know. I didn't do the computations. I don't know exactly the answer. Well, there are 2 minutes left, guys. So probably we can do this very quickly in the last 2 minutes. So first, you have to describe your region D using two different ways. So your D is of type 1 and also of type 2, right? So let's say if you describe D as, so D is just, where's D? Here's D. So you can say, for example, if you start with, let's say, Y, you can say Y is between, where is it? So Y, sorry. So Y is between, this is Y equal to 0 here, and here, let's say, so Y is equal to 0 here, right? Here's Y equal to 0, and here Y is equal to 1, all right? And then X, your X would be between this segment here. This is the line X equal to 3, right? And this line here, so this is the line Y equals to 3x. Okay, so you can say, well, Y is between 0 and 1, and X is actually between Y over 3, because you have to solve for X, right? So X between, Y between 0 and 1, okay? And X is actually between, so this is Y equals to 3x, but if you solve for X, that will be Y over 3. So here's Y over 3, and this is X equal to 3. So this is X equal to 3, right? So all you have to do now is to integrate. So so D can be described, for example, as the set of points Y between 0 and 1, and X between Y over 3 and 3, right? Where is it? Yeah, X equal to 3. All right, and all you have to do is So the double integral of x dA. So you can integrate first with respect to with x first here. So my function is x. So x first, and then y. So we said x is where's x? Yeah, so x is between y over 3 and 3. Y over 3 and 3. And then y is between actually 0 and 1. Right? And then etc. So then you integrate first with respect to x, and then with respect to y, right? First with respect to x, and then with respect to y. Anyway, guys, I'm sorry. I'm going to probably stop here. But next time, I will probably come back to this next time, and then I'm going to show you why this is sometimes useful, having two different ways to compute this double integral, all right? And then I'm going to move to the third, to the triple integrals, right? All right. So, and I will assign the first homework probably on Thursday. Okay. All right. Thank you, guys. I'm going to stop here, and I will see you on Thursday. So take care, everyone.
Okay, thank you. Goodbye.
Goodbye. Thank you, guys. See you on Thursday. Stay safe.
Thank you.
Thank you. Thank you, Enrique.